computer. Okay, so we're recording now. So I guess that means we've formally started. So you're all very welcome to the September edition of Dublin Data Science. This is kind of a talk as opposed to, oh, someone's got a lot of banging. Is that you, Si?
Not me, no, I'm not.
Oh, that might be Niall.
Okay.
So yes, we have a talk as opposed to a workshop. So for once, you guys all get a break from listening to me yabber on for 2 hours. Instead, we're going to have Sci educate us about, well, gradient boosting and trees and all that kind of stuff. So Sci is a guy I met when I was working in London. He works in insurance as well. And he and I immediately bonded over Bayesian hierarchical methods. And we pretty much argue incessantly, although we'll try and keep it civil for the purposes of Dublin Data Science and explicit warnings on YouTube. He's someone I've wanted to have talk at Dublin Data Science for ages, but obviously travel to, Dublin always caused an issue because he has a small family, young children. That's, puts a crimp in your Playboy lifestyle. But now with the benefit of COVID, the very small silver lining is that we can kind of have speakers from further afield. And actually, the speaker for next month is a guy called Jonathan Adams talking about like simulation and stuff. He's going to be talking to us from Texas. So that's, I guess, there's one minor benefit of having having to do everything virtually. So I'm not going to take up much more time. Sci is the group actuary at Optio Group, who are an MGA. Have I got your title right?
Yes.
Group actuary, yeah. And yeah, like myself, we share a strong interest in statistical modeling, solving problems, doing a bunch of stuff. This is some work that we've been talking about for a while, but he knows way more about that topic than I do, because basically my plan here is to shortcut him teaching me a whole lot of stuff in the format of a talk. So I'm really looking forward to it. I'm going to be asking questions, and lots of them during the talk. For the rest of you, if you have any questions, like I'm going to just cut across them, because the one issue you do have with these kind of virtual meetings is it just gets a bit messy from a coordination point of view. So if you have any questions, pop them into the chat and I'll try to ask them like as quickly as possible. But if it's a bit too much of a tangent, we may have to leave it towards the end of the meetup. But that's kind of enough for me. We will, at the very end, I'll give you some updates on what Dublin Data Science is going to be doing for the next few months. But other than that, I am going to turn off my video, put myself on mute, and hand over to Sci.
Okay. It's a pleasure. An opportunity to talk about gradient boosting, which I have indicated is, over recent years, you might have thought was the only kind of machine learning model you needed to know if you're a data scientist. And if you're an aficionado of Kaggle competitions, you would have seen how the vast majority of people for a while were winning the Kaggle competitions by just applying a relatively generic XGBoost model. And XGBoost is one of the most famous.
Just to say that you're also showing the next slide. You're in that weird kind of.
Oh yeah, I was trying to figure out how to not do that. Maybe
that's what it just occurred to me. If you go to display settings, I think it might have the top there. You see there's display settings there at the top.
Display settings.
Yes, you've show taskbar display settings.
View.
End slideshow. There we go. Yeah, and if you go to slideshow, I think it is. No, if you go to slideshow along the top beside animations.
Animations.
So file home.
Oh, right, slideshow.
Yeah.
From beginning. And it goes straight to there.
Yeah.
Okay, something may not work shortly.
If anyone else has much better PowerPoint food than us.
Yeah, you see display settings. You see taskbar, show taskbar.
I now would know what the problem is. It's actually to do with the fact that it's on my other screen.
No, that's okay. That's okay. You can swap them. Go to display settings just above the time there. You see where the time is ticking?
Time ticking.
Top left corner.
Oh yeah. Show taskbar. Display settings. Right.
Click.
Swap presenter. You can see I've not done this with this version of PowerPoint on 2 screens before. I'm being surprised.
There we
I
go.
actually have
Thank
three
you,
screens
Thomas.
in front of me today. Thank you for the tech support. That resolves that immediate issue. Right. Okay. So thank you, Mick, for alerting me to that problem. So back to XGBoost. I'm going to try to cover a lot of bases with this presentation in terms of skill level. I have been doing some research in gradient boosting recently, and I don't know, it's one of these areas that a lot of fruit can come from blending machine learning-y type skill sets, which are a group of people who are more pragmatic, come up with an algorithm that works, and then publish the algorithm based on the fact that it works really well. But there's also the group of people who are Bayesian statistics specialists who like to apply a more rigorous kind of thought pattern to what you're actually solving from a statistical model perspective, which doesn't often turn up in the descriptions of gradient boosting and other tree-based methods. So I'm going to try and blend these ideas today. But when you do that, it's a little bit higher brow. It's a little bit more involved mathematically. Yet I'm doing a no math, no boredom through formulas method. So I'm going to swap to my other tablet here and try and do diagrams and see how that goes with people. And if you've got questions, please make Mick aware. He's playing the role of mediator in terms of how and when to ask how many questions, so that we can kind of modulate how fast we progress. So
Yeah,
I just have a very
just from a practical point of view, I can't really see the chat.
I do see
full
something.
screen.
I'm not really looking at it.
Yeah, so I'm just going to monitor the chat. So anything you want, just pop it in, and like I said, I'll try and get to it as quickly as possible.
Thanks. So yeah, I have a very simple agenda, right? So first off, we start with some definitions. Now, for any people who have an interest in this area, I really strongly recommend you go to the wiki page for gradient boosting and boosting. It turned out that you can often be disappointed by the wiki page in terms of just hitting you with a wall of math and things like that. And I was pleasantly surprised with a bit of history, introduction.
I actually read about that a while ago. So it's kind of a known phenomenon, particularly in the sciences, because basically it becomes an ego thing. So people try to write it as technically correct and as accurate as possible, and make it completely inscrutable. And when you try and fix it and simplify the questions, all the keyboard warriors get really mad and revert the changes and all that, and people make it their mission to maintain pages.
That's right. And I had the most hell of a time trying to figure out a simple idea of what a dot product was. If you go to the wiki page for dot product, you will get drawn down a tunnel that you don't want to go down. And, the wall of math will hit you, and you'll be in Hilbert spaces and you won't know why. And you're just trying to figure out what the dot product is. So there are some challenges in some areas of wiki, but in this area, it was great because you could look at some history and understand some general principles. So I've got some definitions, and then we're going to build a tree just for those people who don't know how trees kind of work. And I'm actually going to do that from a different perspective today. So I'm going to actually show a version of what I read in an introductory research paper on how trees are understood by statisticians versus the machine learning representation, which is what the vast majority of representations on the web are. If you go to YouTube and try and get a description of how to build trees, you'll get a simplified view. So I want to expand our horizon a little bit at that stage. And then we're going to move to multi-tree models, and we're going to talk about random forest as the basic tree model. Then we're going to try and bridge that across to gradient boosting, or what boosting means, and what then gradient boosting is, and then what gradient boosting applied to trees is.
So sorry, just so I'm clear, because I guess, and I'm actually, this isn't a tee-up question because it's something that's occurred to me. I remember when you first started looking at this, one of the discussions we have is that essentially trees and tree-based methods were essentially, for want of a better term, astatistical, that there was no real statistics applied. It was purely kind of an algorithmic computer science.
It was designed because it was fast, it was easy to implement, and they could churn through bazillions of data points and get a result that seemed to work. And they would pragmatically write papers on the basis that, hey, look, our train and test results are really good, and this is now state of the art as a method, but don't ask us why it works. Just know that it's the best. And I
So
think
and always they always said
90%.
that there was no statistical models being done. Like it wasn't done. You couldn't really understand the statistics for it because it didn't.
When first
it wasn't
proposed, no.
exactly, yeah. So has this been a very recent thing then? Have people just kind of maybe with the success of boosting in the last few years have
No, I don't
started
think
looking
so.
at it,
I think
or
progressive. I think a machine learning person comes up with an algorithm that is a twist on a previous algorithm, and they go, "Oh, look, it's cool and it's state of the art," and they publish. And then Bayesian people come out later, like years later, maybe 3, maybe 5, and go, now I understand why that model works. It's because of this and this and this thing. And if I re-express how you've actually talked about your method in terms of a Bayesian framework and statistical distributions, I now can derive why your model works the way it does. So it takes a while for people to come to terms with why it works. Right. But they generally get the practical implementation first and the explanation later.
Right.
And this definitely is true for gradient boosting. Gradient boosting, initially won the Godel Prize, but then, oh, that's my daughter in the background yelling. That's good. That's going to be fun on a YouTube channel. I'm not going to brush my teeth and things like that. Because
well, she's gonna love this video in a few years' time. Let's just pay. She's taking out a loan that's going to get repaid with interest.
So, so I have doubled down on that because I'm a Bayesian aficionado and I care about explanations of things, because when explaining it well, you now broaden out your understanding to include it among a number of other different ideas. And you can put trees now in a kind of a different way of thinking about them, which includes a bunch of other models. And trees become a simplified implementation of other models. And that has allowed me to do some things like I've done on my GitHub, which is where I've implemented random forests from a Bayesian perspective with some approximations, which look very much like other kinds of models. And you kind of go, okay, so once you get a little bit of a broader understanding, things start to come together quite well. So I'm going to try and give that to the audience today to some extent. All right, let's move on. Click, please click. There we go. Definitions. Did we miss? No, but definitions. Okay, so boosting. Boosting was a idea initially, and in fact, it was posed as a paradoxical challenge. That people wondered whether you could bring a whole bunch of, there's a whole bunch of jargon in this statement, right? High bias, low variance, underfitted models combined to low bias, low variance models. Like, well, what's all that? You have to be aware of the bias variance trade-off, which I might try and allude a little bit to in this talk. I'm not so sure people are very strongly aware of how that turns out, but let me just say
most people are side, but I would assume
great.
Go over it anyway. Go over it anyway, because it's worth like reiterating.
There's various levels of explaining the bias variance trade-off, but the most simple idea is that if you pick a very simple model, it'll give you pretty much the same answer all the time, because it doesn't have the ability to give you different answers because it's a terrible model. And that will give you a systematic error. It'll give you an error that isn't quite near the truth consistently. So that's bias. Bias is essentially a systematic error in your model due to a poor model with bad assumptions about the data. And as you improve model complexity, bias tends to go away. So you enter into a situation where you're generally emulating the true behavior underneath the data. But if you keep going too far and you add more and more complexity into your model starts to jump at shadows. It sees a random noise spike in your data and then tries to add more complexity to fit that spike, when that spike is just spurious. It's just a happenstance of statistical randomness. So you end up into a situation where you get a model that has limited bias, doesn't have a systematic error, but it's trying to fit all the noise, and that's generally described as overfitted. And that generally will have a high variance, meaning it will jump at all the noise in your model and it won't give you the average result, which is what you need if you're going to do an out of sample test. because out of sample tests, it will be poor if your model's adding a solution that includes some random noise. So it tends to add more noise to your out of sample tests. If that makes sense to people, you know, it's hard when I don't have any nodding faces and body language. But that's the broad principle that people kind of start with, and they say, well, what if we got a whole bunch of stupid models that all have different but high biases? They're all stupid models, but they're all different and high bias, and maybe they can get a bias in different directions all around the true answer, and somehow you can bring those high bias models together to get a low bias model that also has low variance, because every individual model had low variance to start with. So arguably you could possibly get a low bias, low variance model, the best of all worlds, by combining a whole bunch of stupid models. That was posed as a dilemma. And arguably, that's the definition of boosting. Boosting is any situation where a number of high bias or low complexity models are combined. It doesn't even specify how they're combined. It just says that when you do this combination process, that's boosting. So random forest would even qualify for boosting if random forests were made out of very, very small trees that had very low complexity. So if you made a random forest out of what's called stumps, meaning trees that have very low complexity, you would have a boosted, so that would be a boosted model. But random forests typically don't have
the way it was, someone once explained boosting to me. They said basically that if you've got a tree, basically what a random forest does, with a random forest, you have basically a load of low bias but high variance trees, and you combine them together to reduce the variance.
Yes, the opposite.
Whereas it's the other way around with boosting. You have very high bias but low variance trees, and you combine them together to reduce the bias. Peter, I just saw your question there. Is random forest not bagging? It does use bagging, yes.
Yeah,
but it uses a couple of other things. It's not just bagging of the rows. It also uses the bagging of the variables at every decision point. Random forest was actually genius. The more I learn about the random, I mean, it's so simple. It's one of those things that it seems blindingly obvious when someone explains the idea to you, but like a lot of really genius ideas, it took a genius to think of it. Whereas boosting is kind of the other way around. Like I said, it's got a whole load of really, really like crap low depth trees, but then combines them all to reduce the variance. And once kind of I think it was Martin O'Connor, one of the guys who is a regular on before COVID, he explained all that to me, and from that point on, it kind of made sense.
Right. So yeah, that's the main point. And so when you talk about gradient boosting, what are you talking about? Well, as we've defined boosting quite broadly, there's a subset of boosting methods which say, oh, the truth behind additive trees is that they can be expressed as correlated to the previous tree, and adding something that is more like trying to modify the solution of the first tree to make it better. And if you think about this is a function that is trying to iteratively get better with each step of the process, then it's more like a gradient descent. It says, okay, I got a function, it's partly good. What can we add to that function to make it better? Meaning it's the gradient descent towards this definition of better. So if you define the function that says what better means, then you can define how to do a gradient descent to make the fit better and better and better towards that. And if you make the most simple assumption that everything's normally distributed and you're doing the least squares fit, then the most simple version of gradient boosting is that you say, oh, well, you fit a tree, and then you fit the next tree to the residuals of the first tree, meaning whatever error comes out from the difference between what the tree says and what the truth is, or what the sample says, take that difference and then fit the tree to that difference, fit the next tree to that difference. And so gradient boosting is born out of the idea that you're going to say, okay, add a tree and then add another tree to the residuals. And maths, and it depends on how much interest there is in going through the math, but the math of a normal distribution fitting the residuals turns out to be exactly the solution of what you should add to a function when you're using least squares as your error term, or as your error function or your loss function. It's exactly what you should add to best gradient descent the function. So if you were going to say, okay, what do I need to add to this function to make it correct or perfect? Well, it needs to fit all the residuals. And if it does fit all the residuals, you have perfectly improved this function. And so what this turns out to be then is, instead of this, okay, we're doing iterative trees that add together and it's an additive model, which I'll get into a little bit more detail about later. It turns out to be, it's functional gradient descent. That's what they describe it as. They say we start with a function and then you determine what you need to do to change that function to improve upon it. And the best thing you can do to improve upon it is add some equation, which is the gradient of, I won't get into it, but the gradient of the difference between where it is and where it could be to get the best solution. That gradient is exactly the residuals in the normal distribution case. So,
and just to ask, Cy, I have a question coming in there. How would you define ensemble models compared to boosting?
Well, boosting starts out from the principle that all those ensemble models have to be dumb, really simple. So it wouldn't be boosting if ensemble models were all complex, and they typically are. So ensemble models are not boosting because all of the various components of an ensemble are in themselves quite complex, meaning low bias, high variance models. So they more are like the random forest in the sense that they're trying to do a whole bunch of different complex models that are all high variance and then somehow combine them to reduce the variance.
Right. Okay.
Okay, so looking through here, we've got a concept that the booster models are built by adding successive simple models to the previous iteration. At each step, the model is made up of a larger number of smaller models. This additive model is more adaptive to the failures of the previous iteration, so it differs from random forest in that respect. And in the usual case, the next model is built to reduce the residual error of the previous iteration. Right? So we're talking about residual errors progressively being fit at each step. So gradient boosting in trees is, okay, well, if the model that you're talking about, that you're trying to fit with, is a tree, then, okay, you've applied gradient boosting to tree models. But trees are not the only way to do gradient boosting. And as you see now, the boosting, gradient boosting, and gradient boosting on trees are all progressions of an idea. Okay.
Yeah, when I was actually at a conference in Georgia a couple of years ago. Basically, some people actually use boosting on linear models, believe it or not, which I didn't think was possible because.
So now we know.
We can do
simple GLMs. We could do,
but what basically, because linear models are additive, boosting is kind of pointless. But instead, what they would do is they would use it on L1 and L2 regularization, which isn't additive. So they would fit a succession of L1 and L2 regularized
to the residuals.
And the speaker had actually done that and said it had actually produced pretty good results.
It does work fine. Yeah. So I read that paper also, and I was like, okay, it's a revelation to me to see that in truth, when you're trying to add something to a previous function, so you're creating a function, a piece that adds on to another function, then this is sort of like a perturbation on the previous function. That process is obviously different to just doing random forest or independent models. So this dependency is very interesting, and how to track it and how it works in practice is obviously the underlying principle of why gradient boosted trees works as a principle. Now, AdaBoost being the kind of the first of its kind in that arena, or I suppose you could say that, won the Gödel Prize, but in 2003. So this shows you how old this principle is. It's a while. And XGBoost is a relatively minor upgrade on these main principles. Okay, so I have here all sorts of fun. Ooh, come on, this should play too. No, all right. So I have some animations here about how trees get built, but I was also going to draw a diagram for people. But I want to, like, there's no way to raise hands or anything. And, you know, there's a lot of experienced people here and a lot of relatively junior people, I imagine. And we want to kind of just generally kind of look at some trees. So
actually, sorry, that's not a bad idea. If anyone is completely unfamiliar with all this stuff, just if you're not comfortable putting it into the public chat, you can send me a direct message. But if anyone, I was going to assume that at least people don't have a basic understanding of trees here.
Yeah, because I could skip past like how to construct a cart, a cat, you know.
But I'm going to make the assumption, looking at most of the people here, I know a whole bunch of the names. So I think most of them are pretty familiar with it. But if not, if you'd like Cy to go over some of the basics, just shout out in the chat. That's what it's there for. Otherwise, I guess we can skip on.
Right, so classification and regression trees, CART, is the fundamental here. And you can see an example on the top being built. Now, building a tree is a question of a number of different assumptions about what you're talking about when you build a tree. But the most important thing that a lot of people talk about, which I actually now disagree with, which is great, is that at the bottom of a tree are leaves that have one number, typically, about what the answer is. And in truth, that doesn't have to be true. And I'm very interested now in how to kind of construct models that at each leaf give a model. So how I was thinking about trees now is that every leaf of a tree is actually, in the canonical case, it's providing the main parameter of the model, which is often just the mean of the data, the average expectation. But the leaf of a tree can supply you anything that you were looking for. And so in a paper that I saw, at each leaf of a tree was a separate GLM. So you could come down to a solution that had different GLMs for different locations in your feature space. That's really what I want to talk about. But anyway, so let's say, okay, I'm going to build it with log likelihood rather than just kind of the basic approach to fitting averages. And the data treatment.
So just to iterate that, because I think that's an interesting point. So what you're basically saying is the leaf of every tree could, for example, have a mean and a variance. So therefore,
any number of parameters and can have any distributional form, which ultimately means any model.
Right.
So you could have a tree with lots of different models in it.
Okay. And sorry,
but the thing that I was going to start from is the idea of the log likelihood, which is kind of ignored in this process. It sort of says, oh, the mean in this area is that, the mean in this area is that. And I'm like, well, that's not how best to describe how this is all working. I think.
Unfortunately, I think I had a little bit of Wi-Fi issues there, so I think I'm getting a couple of chats messages here. Is that what a M5P model does?
Oh, I'm not familiar with that term, M5P.
That might be worth. Yeah, that might be. Peter, if you don't mind hanging around after the talk, I'd be curious to know what that is. And then another question was, can you define that distribution? I'm not quite sure, Greg, what you mean. But I presume you could,
I will actually try and draw it for you. That's why I have my little tablet here, so we can talk about what it actually means.
Just to go to my point, I'm sorry about that. Yeah, for each leaf, I presume, and each leaf could have a completely different probability distribution with different parameters as well, right?
Different parameters.
So essentially, if you go that way, what you're essentially defining is an elaborate mixture model.
Yes, you are defining
under that. Okay. And then finally, there was another comment there. Could you please also put these papers you talk about later in the comments of the meetup or in the presentation, the Georgia Tech paper and the ones that talk about leaves being models? Yeah, that's not a problem. I presume do you have those?
I'll have a look. I don't know. Yeah, the leaves being models one was one of the 100 of papers that I have flashed over in the sourcing for this presentation. So I will.
In principle, we certainly can, and I'll try and get a bunch and probably put them up on.
I'm going to make it obvious to people, but yes, the one that you're talking about that made the log likelihood very clear, and the fact that at each leaf, the log likelihood statement just has to be able to be made, which is a very strange situation. It's not talking about an average. You just have to be able to write down a formula for the log likelihood for each leaf. It could be any formula.
Yeah,
and
sorry, Peter just came back. The M5P model, it's a decision tree with linear regression at each node. That sounds like what you were talking
right.
about.
Yes. Now these are, each node has its own model, and then the subsequent nodes are additive, I take it. And so then you have the upgrade, I suppose, the slight upgrade to XGBoost, which is that you traverse through the tree, and at each node you get an additive new step to the model. So as you get to each leaf, by the time you got to the leaf, you have added several models together. Now this, in principle, is the same thing as a normal tree. It's just that the model at each leaf is expressed as how you traverse the tree. So this is just about using a tree to represent ideas. So this is the thing I want to make clear to people. The tree isn't intrinsic. It's like a way of thinking about the work, the math. Anyway, I don't want to get too diverted for the moment.
So what you're saying is that the tree is a model.
The tree is a model of the model. Yes, it's a way of thinking about the model that makes it easy to understand the mathematics and represent it to people. But there are other ways to represent it. And so I kind of have gone through a bit of that in my time now looking at this work, and have seen a few different ways to express, for instance, XGBoost's technique and method can be expressed as a successive tree. So you can turn an XGBoost model or an additive tree model into just one tree. And you can then say, oh, the XGBoost model's kind of a simplistic implementation of a more complex version of the same implementation in a tree. So I don't want to seem esoteric, but the point is that there is a few ways to look at this, and I wanted to draw that out for people in a few diagrams when we get around to it. I just want to cover off some of the major kind of commentaries on tree construction. So if you're going to build a tree, right, it needs the features, and typically you have to treat your features like, for instance, categoricals have to be turned into one-hots. And because trees by their nature, which isn't absolutely true, but often by their nature, only split on one feature at each node, then if you know stuff about your model or about your data where specific features will be really smart, and there's correlation in your data or things like that, then you should put those features in. So if, for instance, considering a GLM, if you're going to write a GLM and you say, oh, well, it's, I've got features A, B, C, D, but I know that B and C are interaction. So I'm going to put in an interaction term. I'm going to put B star C or B times C in as a feature. So you then add that feature. So in a tree-based model, you would go, okay, I've got A, B, C, D, but I'm also going to add a feature called B times C. And I'm going to add C squared because I know there's like a curvature, and I kind of feel like I should add that as a feature so that the model can see that easily. And then when you do this idea and you put these other features into your model, it's interesting. Then you're kind of giving your model an easy way out to fitting nonlinear terms, because the tree is intrinsically linear. It's intrinsically unable to do anything too heavy. And this brings the principle of feature engineering into the tree structure process. So if the tree is not allowed to do nonlinear stuff, you have to explicitly give it which bits of nonlinear you're going to allow it to split up. So I just made that point, wanted to make that point. Now, when you're building a tree, you have to choose the structure and the method. Now, let's say that's a hard concept, because the ways of building trees are kind of myriad, and the methods for building trees are kind of myriad. And the simplistic stuff about trees is that, oh, well, I'm going to have a binary tree, meaning you make a choice at each node and it splits two ways. That's not fixed. You didn't have to split just two ways. You could have split several ways, but binary trees are the first step typically. Oh, it's acyclic, meaning, okay, there are no bits where the trees join back together again. That would be a bit unusual for trees, right? So in sense that you make decisions and they are linearly progressive. And the next step is, oh, well, hang on, what about the fact that some parts of the tree can't break into other bits, but other parts of the tree can break into additional pieces? Is this, how do we make the decision as to whether to split or not split on a particular branch? So there's additional methods, for instance, like, oh, well, if we were going to do a split at this node, it better improve the log likelihood when we do so. And if it doesn't improve the log likelihood by a set amount, then don't perform the split. So those are kind of choices in, okay, well, how many nodes, how many levels in the tree, how much to split by, what are we actually solving for at each of the leaves? Like, is it just the mean? Or are we going to solve for the other parameters simultaneously? And how are we going to regularize, or what's the method for solving the tree? Is it going to be like maximum log likelihood? Is it going to be in a categorical example where you just have plus and minus counts? What kind of method are you going to come up with for doing that? So there's quite a lot to choose from, broadly speaking. I like, in this conversation, we're going to be talking about regression. I think that's a broader sense of things. And typically you're trying to find out a cost function, and a cost function for a lot of people is just something like least squares, but least squares can be expressed as a log likelihood with a normal distribution and mu and sigma. And if you do that, it becomes kind of immediately obvious that you're forcing that sigma is a fixed number throughout the model, which for heteroscedastic data may not be true. So sometimes you go, oh, there might have been a better way. So that's the principles of building a tree.
Sorry, just to go over that point again, just because I think it's an important one. Just when you're fitting for their mean, you're assuming basically, like you said, a homoscedastic. So you somehow then kind of put the parameter in as the sigma goes in as a single parameter rather than having multiple parameters. And I guess there's lots of ways of changing that and adding sigma in there, but typically it's harder to fit variances than it is to hit means. I know I've built a lot of Bayesian models where as soon as you start doing any kind of interesting work with the variance, the whole thing explodes.
Yeah, which, conveniently just ignore it seems a bit sad. Yeah. I kind of feel like, well, no, you should start with the principle that you did have a sigma.
Yeah.
And if it is heteroscedastic, there may be an intelligent idea behind trying to understand what that sigma is. I know in the Bayesian world, that's important for trying to determine parameter uncertainty and fit accuracy and out of sample performance, and also the generative component of these models if you're going to turn them back into data generators. So it's a whole bunch of things in there, right? And
yeah, well, the other big thing you've got to remember is if you're allowing variance to vary, that can have a very significant impact on the mean. Because if suddenly your variance isn't unique, then suddenly, if you can have different, even really simple, like if you've got a categorical variable and you allow the variance, you just, let's say you have 5 categories and you're going to have 5 different variances and everything else is the same. That could actually have a significant impact within those categories because you're not forcing this homoscedasticity anymore.
Yes. So that's what's been throwing me about this, the way people are taught the models is that they, the one on screen, everything that's on screen here and things that you'll see on the web are all like, oh, well, the leaf has a single number. And I'm like,
sorry, we have a question coming in here. Yeah. Are there general tools to look for these? I'm not quite sure what you
like Greg. If you're going to try and apply there are standard methods for doing cart in R that you didn't have to know any assumptions. You just go, give me a tree fit to this thing and it'll do it. Or a random forest, give me a random forest. And it's like a one-liner. The problem with these models and methods that are available in R and Python, etc., is that they abstract away all of the interesting ideas that are contained in how they're implemented.
Yeah, sorry, he clarified there. It says in order to go from homo to heteroscedasticity. So there's things like generalized least squares, and there is a bunch of methods out there that do deal with, like, they relax some of the assumptions of the models. The problem
XGBoost allows you to write out whatever cost function you want.
Yeah.
You just have to get under the hood, right?
The typical difficulty you have, though, is that you have to be careful because they're typically implemented in a kind of a recipe fashion.
Yeah.
And then they don't work properly. And then you're kind of bunched because you're like, oh, crap. and it becomes very apparent that you don't really know what you're doing, or you don't really understand what you're doing. And I'm not saying that in any way to be scathing. It's just it's a very easy trap to fall into. So you just have to be a little bit careful. But sorry, I'm hogging, Si. I'll let you.
No, I like this interaction. But the point is that the simplistic way of thinking about it allows people to not get into too much trouble too fast. But if you look at the broad implementation of how this works, you aren't limited in the ways that are broadly presented to you. And if you did explore how to, like if you wanted to split 3 ways at each node, like what are the implications of trying to do that? You'd have to have 2 different cutoffs solved for at each node. Oh, is that something that we want to do? Or is that best left as a binary tree method? And if at each node we're not splitting on a feature, but we're allowed to split on a combination of features, right, which is a GLM, then there's a GLM feature construction at each node. And how do we solve for that? And how do we make that stable? I suppose is a nice way of looking at that, because then it's not necessarily identifiable as a model. So what I mean by that is you'll come up with unidentifiability. There are lots of ways to build a tree that produce the same answer because of very small variations in how you do your GLMs. So, in a way, trees force simplicity, and by forcing the simplicity, they get to a solution that you can't accidentally get wrong too easily. But if you do choose to generalize, how do you? Now, I was struck with that problem. And what I did is I was very interested by the problem of trying to introduce trees into Hamiltonian Markov chains, which typically have to have a smooth environment and can't ask questions yes, no. They can't do yes, no questions. They can't make if statements.
Sorry, as Neil just said there, that I think combinatorial explosion is why binary splits are the default option. I would tend to agree with that.
Yeah, that's a good point.
2 to the power n is, as bad as it is a lot better than 3 to the power of n.
That's a good point.
So,
there's a lot of these like under the hood considerations when people just kind of throw random forest at a problem and they don't really think about it. And I'm like, well, yeah. Is it worth thinking about it? That's the question we ask ourselves. Early on in our career, we might go, oh, I just need a solution quick by today. And then later in your career, like where I am, you kind of go, no, I'd like to understand why I'm not able to do these solutions in different environments. And so when I pursued doing trees inside Hamiltonian Markov chains, I was struck with trying to understand how to do feature selection in a smooth way and if statements in a smooth way inside other types of models. And this is more about the idea of embedding. So I wanted to embed a tree model inside a more comprehensive Bayesian model. Say I understood the distribution of my data, but I understood it up to a point. And then I thought, okay, well, but there's some segmentation in my feature space that I just want to throw a generic treatment at. Like, go find me segmentation on feature space that seems to work reasonably as a starting point.
Sorry, I think my internet is just a little bit flaky here, so I think it gets a bit jaggedy. But we have another question here that Thomas has said. Can I ask what problem you were applying the MCMC to? Like, what was it that prompted the use of trees?
Absolutely. So for me, it's severity distributions when you've got large feature spaces. So at the moment, for my last year, I've been working on cyber insurance. And in the cyberspace, you can get feature spaces for each of your insureds that are quite large, involve a whole bunch of stuff. You can get data from other third parties about, okay, what kind of
just to say, so you probably assume that most of the people here don't understand insurance, even though I mention it a lot.
Sure, okay.
You might want to explain the consequences of all that.
So when you are providing a cyber insurance policy to a small business, in my case, and small businesses anywhere in the world, you have to try and consider the risks that they might face. And one of the challenges inside that space are that there are some features that are correlated with the severity of a claim. The larger the business, the more likely the claim will be large. There are other features that are also important, like it's hard to go into all of them, but there's things like, do you use do you use Zoom when it's unprotected and has some challenges around what they call RDP exposures, which is like you've opened
desktop protocol.
Yeah, remote desktop protocol ports have been opened in your firewall to allow the transport of the video, but because this has got a remote desktop capability in it, then someone can piggyback into that, somehow tunnel through into your computer and hack it. And ransomware has been taking advantage of that in a number of cases. So we noted that for some companies that do have RDP port holes, exposures, they are more at risk. And we could actually measure that. So that becomes a feature that you can add to the policy. So when you have all of these different features, some of which are categorical, yes, no, some of which are where in the world are you, some of which are how large are you, how many employees do you have? You have all these feature spaces. And then I'm trying to solve for the severity of the claim. Now, the severity of the claim I already know is log normally distributed with a Pareto tail, which has 3 parameters. So I know the severity model is not normally distributed. It can't be converted to a normal distribution in any way. You must leave it as the log normal Pareto form, which is a 3-parameter model. And I was struck with, oh, well, why can't I use a tree to solve for those parameters? And the truth is you can totally use a tree. It's just that inside a stand model where you're doing Hamiltonian Markov chains and you're going to solve for the severity of the parameters for the severity of the claims, you don't get trees. You're not allowed to put a tree inside a stand model. You can't. It's one of those things that hasn't been done. And I'm like, oh, why hasn't it been done? Like there is a thing called the Gumbel Softmax, which allows you to approximate a one-hot inside a stand model in a smooth, regular, like a non-centered way, which is a term I don't know if we want to go into. So you can generate one-hots that are pretty good, and they have you can dial up the accuracy and dial down the accuracy using temperature score. And with that, I can do feature extraction, I can do feature selection, and I can do all the implementation components of a tree inside Stan. Why don't I just do that to just show that it can be done for people and demonstrate how you can do trees inside Stan, and that you can use the tree to solve for instance, the log normal Pareto's parameters, in my case, were mu, sigma, and alpha. So that's the problem that I was facing, is that I had a real world example where it did not follow a normal distribution. The data set was relatively small, so I wanted to use Bayesian techniques to regularize and also diagnose problem fit. And yet I wanted to implement a tree to solve for my parameters. So I was forced to go and do this myself. So as far as I know, in the first person who's written a random forest implementation, I've yet to add the gradient boosting component, the random forest implementation inside Stan, such that you could produce any number of parameters. And that has brought me to this kind of question of this presentation. It's like, okay, well, what did I have to understand in order to implement that, so that I can relay to you the interesting kind of additional options that are there for everybody when they implement trees. And whether the barrier to entry is too high is a question. It's an interesting idea, right? And whether it's worth it, I'm not sure. I can't answer that for everybody. It depends on what you're exposed to. But in my world, the tail of the distribution was very important, and it was intrinsically asymmetric. So none of the standard methods was a good idea. If I just used the tree as you see on the screen here, it would have given me a woefully underestimated average claim size. So much so that I wouldn't be able to use the model, and wouldn't also be able to explain why. So that's an important feature, I suppose, of what drives me in this presentation, to try and re-represent it in a different way. Okay. Any further things there, Mick?
No, yeah, he just said pretty cool.
Yeah, there's lots of stuff like that out in the world. Most things are not symmetric. Most things are not well behaved.
Well, it's one of the things we've talked about before. I mean, one of the reasons why I find insurance so fascinating is that the problems are very, very difficult and very challenging. And you often don't have, you kind of have it. It's not quite as pathological as analyzing financial data, because the world isn't constantly trying to work against whatever patterns you're finding. But you do have the problem of, at least you have a lot of data in the financial world. In the insurance world, you typically have, even if you have a lot of data, it's still not a lot of data by global standards of what counts as a lot of data, and the problems are very difficult, and the cost of getting it wrong can be existential. So it kind of forces you to think in certain ways. I actually can answer that. There's papers on it, Greg. So did you write the cost function for the log norm and Pareto tail? There are a couple of papers out there that do this. Well, I believe you said the math is wrong. I can certainly I'll share some of those links.
It's really easy to do, actually. It's kind of funny. But XGBoost has the intrinsic capability to have any log likelihood function embedded in it if you care to figure out what the hell you're doing. Yeah. It's
if you want to hang around until the end, Greg, we can talk about it. It's kind of a bit off topic here, and I am conscious of the time. But yes, if you want to hang around to the end, we can.
I don't actually have a clock on screen, which is annoying.
5 to 8, sorry.
46. Okay, right. Okay, fine. So most of our talk so far has been about building a tree, which I agree is really important. Like, what are you doing when you're building a tree? It's very important to understand. And I have here some issues around, okay, the maximum depth of a tree, fitting some data on the bottom here. That's pretty important as to how much depth you want in the tree is how simple your model is. As you increase depth, whether the model gets better or gets a bit stupid looking, and might also overfit and start fitting to noise that is intrinsic. And as you can see on the model on the bottom, it's starting to look like it's fitting more noise as you get. It's not necessarily adding value by the time you get to a max depth of 8. I hope everybody understands the depth of the tree being 8 levels long would be 2 to the 8 leaves versus, a depth of 2, which will only have 4 leaves. So the complexity of that, and the fact that when you build a tree, it can only ever slice up your feature space. And in this example, the features are just 2 features. X and Y are the 2 features available. They're both continuous. And trees can only do a horizontal line or a vertical line, can only ever break up a feature environment using parallel and orthogonal lines. So let's move on to multiple trees. So a random forest is a multiple tree method where you use lots of big trees. Big trees meaning you're not really worried about the complexity. You want to make sure that you've covered the necessary complexity for each tree, but each tree is generated off slightly different data. And bootstrap aggregation or bagging is the main principle that's used in random forests to make sure that each tree, although it has relatively high variance, low bias, you want to change it up. You want to increase that variability somehow. And as Mick was suggesting earlier, bagging can be used not just on the basic data that went into the model, but also on excluding certain features. So you can have, randomly select a certain set of features that's available for each tree as well. And some features are therefore excluded on each model.
Because it's actually at every node site, it's not even every tree.
Oh, right, yeah.
Because what happened was, if you don't do the bagging on each node, you end up with a highly correlated trees. So you don't actually reduce the variance. Because even if you're just subsetting across the data, they still essentially encode the same information. So you end up with, you don't end up adding more.
As you progressively choose more features to split on, you're forcing those features to be different features at each layer in the tree.
So every single node, usually it's the square root of n, where n is the number of features available. I think that's kind of the heuristic they use. So if you have 10 features, you select 3. You choose 3 and you split on those 3 only at each node, and then every single node gets another random set of features to split on.
And the question to everybody would be like, why is that workable? Why does that work? What's the point of that? And it's very hard to describe how that works as a regularization technique for making a tree more well behaved on an out of sample test. And it turns out that you're applying a prior on what features and how many features are available to each node. And I had to confront the same thing in my method. I was like, okay, how many features am I allowed to consistently split on it in any given node? Should I have it only and always be splitting on a specific feature, or should it be allowed to choose different features each time we iterate on that node? So I don't want to get too stuck in it, but it's an interesting arena for people to think about. And you'll learn a lot of statistics by just trying to understand why you're going to make one choice versus another choice. So here we have, right, subsampling the data, subsampling the features as well, we've already mentioned. You can have a proposed solution from each tree with different data. Each tree is like a sample from the posterior of all possible trees that describe the data. So I want to be clear about that. When you use bootstrap aggregation, you're subsampling your data typically. And the reason why it's subsampled is you typically want an out of sample set of data that you can say, oh, well, you can do an out of sample test on this tree and say, oh, well, for the in sample data, it gave this solution. On an out of sample data test, you can see that it has a level of accuracy. That isn't the only way to do it, but I noticed that that's what's relevant. But what's also relevant when you do bootstrap aggregation is you've varied the way that the parameters can fit to the data. And here is a description of bootstrap aggregation and why it works. So I don't know if people have people had a description of bootstrap aggregation and why it works. I'll take silence as no.
I'd say make the assumption that you have to explain it, Si.
Yeah. So
Even very
bootstrap
quickly.
aggregation works because if you take your data as truth for a second, like your data is the truth, it is a distribution, then you can say, oh, well, I want to sample from that distribution. So I want to have the histogram of your actual data is the true distribution, and I'm going to take a sample from that distribution, and then I'm going to fit my model to this sample. That sounds obvious, but the point is that I have the truth and I've made a sample. I've made a random sample. And if I keep random sampling from my truth, I've done the equivalent of describing or creating models that could reasonably represent the truth. So as I subsample my data and I have a model fit that subsample, I'm creating a model that says, oh, I'm a reasonable sample of a model that could fit the truth. And that's what Bayesian models are. Bayesian models are the set of all possible solutions, in this case trees, the set of all possible reasonable trees that could describe the truth. That's kind of the intrinsic principle of Bayesianness, is that you're trying to say the posterior density, the posterior density is the posterior likelihood of any particular tree having the ability to describe the truth. How likely is it that this tree is the true tree? And so posterior density is really saying, okay, assign each tree a probability, the probability that that is the true tree. And you can get to that solution by us about going, well, if the data is the truth, then I can subsample the data and get various models, and those various models will be equally likely to be the truth. So bootstrap aggregation, this is my hand wavy solution. Bootstrap aggregation is actually a way of generating a posterior density of trees. So the alternative method, which is what I've done in Stan, is when you express a tree in a Markov chain environment, the Markov chain on that tree is by definition the posterior density. So I don't have to do bootstrap aggregation in a Markov chain. I have to do Hamiltonian Markov chain steps. And that gives me the samples of all possible trees that could be the truth. So you can get at the solution to random forest from two directions. You can say bootstrap, or bag the data and bag the sample feature space, etc., and get the posterior density of the likely trees that could fit the data. Or use a Bayesian model that says, okay, if I can express the log likelihood and look at the posterior density and sample from the posterior density directly, and to do that, it's a bit hard because, of course, you have to express the likelihood of all the various models that could be in the posterior density. So that took the time and effort to be able to express the log likelihood. But once done, you sample from that log likelihood environment, and that gives you the same answer as the bootstrap aggregation method. And that's very interesting to me. I was like, okay, well, these are two solutions, and one is an approximation of the other, and therefore they should be aligned. So when I on my GitHub, that's what I've done. I've put the tree inside a stand model and allowed Stan to sample the trees rather than use bagging to sample the trees, if that makes
And
sense.
just to say, Sai, if for the people on the talk here, if people are more interested in Bayesian stats and Stan and all that, the workshop series in 2022, or at least the first one, is going to be on an introduction to Stan and implementing a customer lifetime value model. The stuff we talked about in the workshop
Okay,
series.
so Stan, not everybody's accustomed to Stan models at this stage, right?
I
So
would assume not.
bit-
A few people are, and
bit
most of the
esoteric.
one are familiar with me talking about it, but I will be doing a kind of a beginner's workshop in the new year.
Okay, it is a bit cutting edge, although it's been around for a few years. Okay, so, right, I make the comment down the bottom just to reiterate that if random forest was only using very small trees, like just a single decision, then random forests would be an example of boosting, but they aren't typically done that way. The typical example is to use, as Mick said, larger trees and averaging the examples from larger trees, and thereby reducing the variance. Okay. So in the solution to random forest, every tree has a vote, and they're all independent. They don't depend on each other. They're built independently from each bootstrap sample. But that's a good thing. And then you get answers on not just your yes, no votes or any particular solution you're looking for. You can also get out of sample tests in every tree. It's quite good diagnostically and works really well, but they're all independent. Is there a better way? Okay. We don't know for sure. So let's have a look. There's some recent research here. I've got, you know, I've been going on about random forest with Bayesian MCMC. Here's some stuff that people have been doing on Bayesian CART, prior specification, posterior simulation, really cool stuff. That's from 2007. I think this is all good kind of current research level statistics for people to be interested in. Perfectly good solution, random forests, right? I give my GitHub here for people who are interested in having a look. That's a little bit more advanced because we're doing that in Stan and using quite advanced techniques to get an approximation of a tree. And so when you approximate a tree, it creates some interesting ideas that at each node, you're not splitting necessarily absolutely on one feature. You could be a slight mixture of features. All right, gradient boosting in trees. Oh, good. On the right, we have an example of a gradient boosting method in play and improving as it adds more and more complexity to the outcome. The originals, it's just an analytic function they give. That's the formula here, but they're trying to fit trees to give the solution there. So can we do a linear combination of trees? How do we do it? Add a boost gives a really simplistic example, and XGBoost built on that idea to improve the implementation. The simplest implementation is to fit successive trees to the residual error of the previous iteration. This is the simple way that everybody tries to describe it, but that is assuming everything is normally distributed, which it isn't typically. There's a learning rate hyperparameter that you have to deal with, which I'll try and describe a little bit more of later, which is that you don't take the full extent of what a tree tells you. You say, oh, well, the tree told me this number is the solution. Yeah, but that tree is not so great. So we probably multiply that by 0.1. So each iterative step of the tree that tells you this is the solution, this will fix everything, you go, well, I don't really give you 100% credibility. I'm going to give you 10% credibility. So at each step of adding trees in an additive model, the tree that you're adding is multiplied by a small number to take away most of its effect. So you think, oh, well, isn't that going to wreck the model? Well, you have to say that in truth, each tree is really terrible. So as you add a really terrible tree, you probably aren't adding that much value. And this regularization idea of just saying, well, I think that tree is probably only worth 10% of what it thinks it's worth. So I'll add only 10%. And therefore you're limiting the gradient descent. So you said, oh, I want to take a step this far. And you're saying, well, that's probably wrong. I'm going to multiply that step by 10%. So you're only allowed to go that far in that direction. And then the next tree will go off in a totally different direction. Say, oh, I need to jump to here. No. Just jump that far. So you'll end up doing a gradient descent process through function space, if that makes any sense to people, in small steps. Whereas the gradient, the intrinsic solution to fitting the residuals, if you took the full extent of it, it would be fit the full residuals as much as it could. So people might be familiar with stochastic gradient descent and other gradient descent methods where that is typical, that you don't take the full answer from each step. You only go a little bit for each step, and you slowly get to the answer rather than jumping at shadows again of any one model thinking this is the truth. Okay.
Well, in some cases they use stochastic as well. It's not even for variance. It's just purely a computational thing. It's like, it's too expensive.
Only
to
partial
calculate
data.
across all
Only
the data.
partial data.
You just sample the data, and then you know that your optimal direction for your subsample is not going to be globally optimal, but it kind of gets you in the general direction.
And this is exactly what they do again in XGBoost and others. They noted that there's no reason why I can't use bagging in an XGBoost model. So you fit to the residuals, but you've sub-selected which residuals. You're like, oh, well, don't fit to all the residuals. Let's subsample them. So, bagging is applied to gradient boosting as well. Same with the feature selection. So you can use all the tricks of a random forest with bagging both the feature space at each node and also bagging the data at each step on a gradient boosted model. You might be like, oh, well, why isn't it the best of both worlds? Well, yes, the XGBoost tended to be a much more outperforming model than models that had come before it. And therefore, that's important for people to note that when you add all these other regularization approaches to XGBoost model, it tends to outperform random forest because it's used all random forest tricks as well. Okay, so writing down the log likelihood, the loss function, where the fitted parameter, usually the mean, is optimized using CART. Now, true to expectations, noting that I'm already done almost enough time, I'm still going to do my diagram just so that I don't fail to do the diagram and leave everybody wanting. So let me attempt to do so. So I've got to stop sharing over here.
Yeah, you need to stop sharing first. And then
I'll screen share over here.
Hope this doesn't explode.
And
something's happening.
Yeah, let's see. Oh, look.
Yeah, I can see a paint here.
So
again, I'm keeping an eye on the chat anyway, so if anyone has any questions,
great,
just pop them in. Or
so in a random forest model, you make some choices, and then your log likelihood will be the log likelihood of a normal distribution will be a constant. The likelihood is e to the negative half x minus mu squared on sigma, if I'm correct. And if you take the log of all of that, you get a constant plus e to the something, which then just makes it 1/2 x minus the mu squared on sigma. So that becomes your log likelihood. And here we have xi. Maybe I've done that poorly. Can I use the eraser? No. So this piece is your log likelihood. Constants are irrelevant. Constants out the front are irrelevant. So you go, okay, well, it's just xi minus the mean squared on sigma. And then you go, oh, well, sigma's going to be forced to be the same number every time. Well, no, you didn't have to. Look, if I'm going to say on node 1, it's mu1, and on node 2, it's xi minus mu2 squared on sigma, there's no reason to eliminate sigma. It's just like, oh, well, if your xi happens to take you to node 1, then your whatever the xi is minus mu1 squared on sigma. And then if you happen to be on node 2 for any xi, then it's xi minus mu2 on all squared on sigma. That's your log likelihood, right? Do people follow that idea? I've written down the log likelihood for a normal distribution instantly. But this is often simplified to, well, get rid of sigma. We don't care what that is. Call that a constant. So it's x minus the mean squared, which, as we all know, that's just squared error. Yeah, everybody follow? So trivial stuff. So if I turn to a log normal distribution, I just have to write down the log normal's log likelihood. And I don't know if people are aware of how quick and easy that is, but the log likelihood of a log normal distribution is, well, what's the likelihood? The likelihood is some constant e to the half, I think half's in there, log of x, right? It's log of x minus the mu squared on sigma. Because in truth, the xi's are all logged. I think that's what it's doing. Correct me if I'm wrong, Mick. I think that's what it is off the top of my head.
Are you sure it's log x?
I do remember log x. I was doing the math. If I reach over here, I can grab the actual math. Here is the actual math I have in front of me. So e to the, yeah, it's log x minus mu squared. Yeah, it definitely is what I've just said.
Okay,
oh, there's 1 over x over here. So that x is over here too. That's the only other piece. So e to the, yeah. Yep, that's right. So you can get rid of all the constants in here because log likelihood would come out the same answer independent of constants. And then you end up with just, okay, well, it's in truth, you're solving for mu minus the log of whatever your x is on x. That's what you end up with. But the point is, if you can write down the likelihood function and you can take the log of it, you can write down the log likelihood function, and there was no need to get rid of sigma. You know, I've got rid of sigma in this piece here, but sigma is evident here. So if I was going to write down the log likelihood with sigma included, I would be just writing, taking the log of all of that and getting rid of all the constants. I go, oh, it's log, it's 1 on x, so that'll be minus x plus log of x minus mu squared, and this piece will be divided by sigma. So you can leave sigma in. So x minus the log of x minus mu squared on sigma. So that becomes the thing you're solving for. And that might look foreign to people here, and I agree, it's not exactly straightforward. It's not as simple as the square difference. But when you're fitting a log normal distribution, if you believe your data to be log normally distributed, that is your cost function. And you can go ahead and just go and fit that. And if you want to assume sigma is fixed, then you can get rid of that and call that 1. But you might notice that the model doesn't work out so well when you try that. Because putting 1 here doesn't necessarily solve for the x part. I know that's rushing, and I'm conscious of the time constraints in the model in our talk, but I just want to point out that there's no reason at each node not to write down the log likelihood for the data, and that when you're trying to get the total log likelihood for a model, then at each step of, here's a piece of data, run it through the tree, get my parameters from the tree, write down the log likelihood for that data point, then move on to the next data point, and it'll be the log, whatever the log likelihood is, that added to the previous one. So you just end up adding all these log likelihoods together for all the traversions of the tree for all your data. It's in fact so simple, you kind of go, oh, well, I could write an algorithm for that. And you're right, you can, you really can. And you might kind of trivialize in some ways how these trees work. And you get under the hood and you go, oh, it's not so hard after all. There's not really that much going on. Just the tricks of the trade in terms of implementing this really fast, which is why I like Stan, because it automatically codes everything in C++ for you. Now, just an aside, just for a moment, let me show one extra thing that I thought was interesting when I read a paper by the same author of XGBoost, who wrote another paper, and when he noted that XGBoost is a stump, and I'm going to go sideways for a moment, and it says, okay, here's leaf 1 and leaf 2. And then the next stage says, oh, well, I'm going to add another tree, which also has the same I don't know why I went 4, 5. I should have gone 3, 4. I'm obviously dyslexic today. But what's interesting, if you're going to take a tree and then add another tree to it, you actually have this. Which this is L1 and L2, and I'll continue with my 4, 5. L4, L5, L4, L5. This just repeats twice. So the solution, actually, if you're going to break that, if you're going to use the traversion of the tree, you can traverse this tree and get, oh, well, my data would traverse this tree, and at each node, I add whatever was at that node. I add whatever leaf 1 was, and then I either end up at leaf 4 or 5, which means it's either L1 plus L4 or L1 plus L5 or L2 plus L4 or L2 plus L5. Those are my 4 leaf solutions: 1 plus 4, 1 plus 5, 2 plus 4, or 2 plus 5. And the author noted this and said, well, that's interesting. These 2 pieces are a repeat. That's a bit boring. Why don't we allow the tree to not have the same repeated component in it for each leaf or each node or each leaf of the previous step? Let's have the 2 trees be different. And so he ended up with a tree that, instead of you waiting to the leaves to get your answer, at each node, it proposed an additive component. So as you traversed through the tree, you accumulated additive components. And you solve the tree the same way, like each successive layer of the tree is solved by us getting a solution to the residuals of the previous step. But I just want to point that out to people as another way of thinking about XGBoost, that XGBoost is successive, simple trees adding to a previous tree, and that's really just creating a great big tree in truth by the end of that process. Does that communicate to people? I know I can't see faces again, so I'm left with having to assume that people are okay with that idea.
Yep. Well, we're getting a couple of yeses in chat.
Okay.
I presume the problem there is you just have a coding issue because you've got to track a lot more trees.
Yes, there's a lot more stuff to keep track of.
You've essentially got a combinatorial explosion again.
Yes. So you've got to go, oh, well, where do I stop this process? Well, okay, but the original XGBoost had the same problem too. It's just had less trees, but you still have like 1,000 of them anyway. So why not compress it and have 1,000 trees, but more like, instead of layering many more layers of the tree, have less layers of the tree and have 1,000 trees more distributed.
More discrimination.
That's right. And when he did that, he found that it outperformed. He said, oh, look, for the same number of trees, this is almost like a compression for XGBoost. So I can get the same solution as XGBoost with less content expressed.
From a practical point of view, it's a more complex implementation. So therefore bugs and, but
increased variance as well. Like you've got a more complex solution. So you're kind of teetering at the edge of, well, should I give up some bias for some more variance and get better? Yeah. And he said it was true when he had stumps. So it wasn't necessarily true all the time when you didn't have stumps.
Right.
So if each tree that you're adding is more complex, but repeating versus not repeating, then it wasn't necessarily always good. But I just want to point that out to the audience that there are people who've thought about this kind of representation in a tree and come up with different kind of things you can do. So, I could have the tree go, okay, well, I have, a tree like this, and then it actually has mu and sigma reported at each tree, at each leaf. So I don't have to report my average. I can report parameters, and those parameters go into the log likelihood. And it just so happens that in a normal distribution, the parameter is the mean. Okay, but for other models, that's not the case. And as long as I can write down the log likelihood, I can implement it this way. And in my case, the example I was talking about before, I had 3 parameters. So I had alpha, I had mu, sigma, and alpha to report at each leaf in the tree. And I just want to make that clear to people that is totally doable. And then, in fact, I can XGBoost that I can have an additive component for mu, sigma, and alpha at each node. And then that's not exactly complicated. It's not hard to implement. It's worthy in terms of skill for developing a bit of matrix algebra skills and a little bit of programming, but once you get through it, you kind of feel good about yourself because you've implemented something that broadly is not seen and not used by like 99% of practitioners, and yet does outperform in a lot of cases. So consider that. Okay, so we'll stop the share. Now I've done diagrams and it has worked. We're very happy.
We're coming up toward the time side.
Yeah, I know. So we'll call it quits. So we've written down how we do it. We've written down what it generally is. We've explored how the log likelihood is anything particular. I haven't gone through the math of how the gradient descent on the function is what you're doing when you add functions to adder functions using a fit to the residuals. But with that proof in hand from the wiki page, and if you're interested, then you can apply that to any function. And I, on my piece of paper here, applied it to the log normal and have a solution for the log normal here in a few lines, which was very instructive for me. I was like, oh yeah, look, you can do it for any function. It isn't actually hard. And I just want to point that out to people that are interested. So which let's script onto. So when you have an XGBoost model now, just for repeating for those people who aren't following, that an XGBoost model iteratively increases the number of trees. So you start with a simple tree, you add a new tree to it, fits the residuals. Then at the next step, you go, okay, well, the solution, the previous iteration is those 2 trees plus this new tree I'm going to add. Okay, so now you've got the solution is 3 trees. Then at the next step, you say, oh, well, I'm going to add this new tree to that. So now your solution is 4 trees. So as you go progressively through the gradient descent process, you're adding more and more and more trees. And so your solution becomes the sum of a large number of trees at the end of the process, and which is very interesting in terms of how that turns out in terms of log likelihood, etc. I enjoyed doing that when I was doing it in Stan because it really taught me a lot about what was important in terms of this process. So I think I'll skip this. We've done this over and over now. So here's an animation of how AdderBoost does it on the left. In AdderBoost, it gave you the one final advantage that it would add credibility to certain data points if you were misclassifying them. So for a classification model, it would be like, oh, okay, well, you get a higher weight because you're wrong. Whereas in a regression model, the closer you are to the boundary, the more important you are. So in that sense, you get a regression analysis which weights data points near the boundary higher than points further away. So there's an example of that on the left and the right. Ongoing research. There's lots of people doing lots of stuff in XGBoost and hyperparameter tuning. There was a great paper that I was just reading yesterday on how they were using Bayesian techniques to get the hyperparameters tuned, yet using XGBoost as a deterministic model, because it broadly, once you specify the boosting samples, then the implementation of XGBoost is intrinsically deterministic. So they could kind of jump over to just using Bayesian methods on the hyperparameters, like how many trees should I use and what should be the learning rate, etc. Cool and interesting stuff. There's also a bunch of work that's been happening on XGBoost on GPU implementations to speed up the implementation there. I'm very interested in that and got kind of hooked into looking at Taylor series expansions of complicated log likelihoods as to whether you could simplify them and then implement them on a GPU at blindingly fast speeds, and what kind of problems that might give to the average person like myself. And we're up to questions. And we're on time because we've figured out all the questions as we went along, didn't we, Mick? Or have there been anybody waiting to throw me a curve?
Well, I guess we'll put out a final call. I am conscious of everyone's time. Let me just turn my video back on here. But yeah, I mean, does anyone have, I mean, that was great, Si. Thank you very much. I really enjoyed that. I learned a lot. We do have a bit of time for questions though. Unfortunately, I do have to head off very shortly. But
okay.
Yeah, does anyone feel free to unmute if you want to, or if you want to put something into the chat. While we're waiting, first of all, Si, thanks for that. This will probably go up on YouTube tomorrow. I had some Wi-Fi issues on my phone, certainly, but I don't know if I had them on the laptop. So hopefully that will. There was just a couple of cases where we lost maybe 10 seconds of you. Maybe people in the chat will let me know if that's the issue there. But yeah, we will have a talk next month from a guy called Jonathan Adams, who again is insurance, but it's not going to be insurance related. It was based around Monte Carlo simulation and managing basically in a multi-machine environment, and how he kind of handles all that and things like seeding and all that kind of stuff. We do have one question actually from Peter. He was saying, what are the differences between light GBM, XG boost, and cat boost?
Yeah, you've got me. Like, I was trying to find that out the other day, and I got into a wormhole. And
yeah,
I was like,
this actually came up in that guy on that talk on boosting I had in Georgia. I was at the Data Fest Tbilisi a few years ago, and there was a Russian guy there who was an absolute genius. Although, as someone pointed out, he actually looked exactly like a young Rasputin, including a couple of very attractive young women hanging around him who were, in fairness, though, his age. But he was a very, very nice guy, and he was big into boosting, and he talked at length about them. He was very up on cat boost at the time, and I think cat boost does a better job for categoricals, and hence the name. But I'm not sure.
Yeah, treatment for categoricals is hard. I think this is the issue.
Yeah.
You're dealing with a combinatorial problem, and there's also treatment. Light GBM has a different treatment for missing data.
Right.
But
Okay.
I'm told that they modified XG Boost to take into account the advantages that.
Yeah. Well, this is.
So it was like, it was an advantage for a
Yeah.
minute, and then no, it was just a switch in XG Boost.
The differences between these, from what I know, is very much in the edge cases. It's in certain, like for the most of the problems, you can go with it's a pick your poison, and I think then for various kind of edge cases, one does better than the other. But I wouldn't like to be. I certainly wouldn't be considered an expert on that. Okay, well, look, we will leave it there. I will stop recording now shortly. Thank you, Cy. I really appreciate that.
Pleasure.
It's been a long time coming. I'm glad we finally managed to do it. Hopefully, we can get you over in person at some point in the next year or two, or once the kids get a little bit bigger. We will be back next month, like I said, with a talk with Jonathan Adams. I will probably continue my workshop because I've got 2 more to do to finish it up, possibly 3 if I just need to pad out the month, because we probably won't do very much in December. But other than that, yeah, I'm going to let people go because I'm conscious of the time. It's 8:30 there. I'm currently on my holidays in America, so it's only 3:30 here.
But I can stick around for a few minutes if people want to ask me some questions.
So what I'll do is I'll stop the recording, I'll stay on, and I might make you the host, Cy, if I have to drop off.
Sure.
And at least that way then, if anyone wants to stay on and chat to you, they can. But unfortunately, I might have to drop off. But in the meantime, I will stop the recording. And yeah, if anyone has any questions or anything, and thank you everyone for coming and staying on. And I hope you all enjoyed it.